Space has a flaw. Physicists confirmed it. The universe stops being measurable at a distance so small it makes an atom look the size of a solar system. That distance is called the Planck length. And the strangest part, confirmed by modern physics, is that the moment you try to look below it, the universe fights back. We are going to travel from the edge of what our best machines can see all the way down to the wall at the bottom of reality. We will meet the scientist who proved this wall exists and got rejected by every journal for 5 years. We will find out what space looks like when you zoom in past atoms, past protons, past quarks, all the way to the point where the rules of physics shatter. And we will face the question no one has answered yet. Is the Planck length a true limit built into nature, or just the edge of everything we are capable of understanding? If this blows your mind, like and subscribe. New chapters drop every week. Stay with us. We begin now. Picture the smallest thing you have ever seen. Maybe a grain of sand, maybe a speck of dust floating in sunlight. Now shrink it. Keep shrinking. Past a human hair, past a red blood cell, past a single atom, past the nucleus of that atom, past the tiny particles packed inside that nucleus. Keep going. Keep shrinking. You still have not come close. The Planck length sits so far below everything you just imagined that comparing it to an atom is like comparing a single grain of sand to the entire observable universe. That is a confirmed fact, backed by physics and mathematics, and it gets stranger the longer you sit with it. Here is the number, described in a way that actually lands. If you took a single hydrogen atom and blew it up until it was as wide as the distance from Earth to the Sun, 93 million miles, the Planck length inside that atom would still be smaller than a proton. That is how deep down this goes. Scientists call it the universe's hard stop, the absolute flaw, the point where space itself refuses to cooperate with the idea of measurement. Max Planck calculated it in 1899 by combining 3 fundamental constants of nature: the speed of light, the gravitational constant. He was building a universal system of measurement, something that any civilization anywhere in the universe could independently calculate and arrive at the same answer. He called it a natural unit. He thought it was mathematically elegant. He had no idea he had just drawn a line at the bottom of reality. The number he landed on was roughly 1.6 times 10 to the negative 35 meters. Written out, that is a decimal point followed by 34 zeros before you reach the 1. Your brain cannot picture that. No brain can. That is part of what makes this so unsettling. Physics has since confirmed that this length is the point where 2 of our greatest theories of reality begin to break against each other. Quantum mechanics describes the very small. General relativity describes gravity and the large. Both have been tested thousands of times. Both work perfectly in their own territory, but force them to describe the same place at the same time, specifically a space the size of the Planck length, and they produce answers that cancel each other out. The math gives you garbage. That collision is the core of the mystery. The Planck length marks the exact address where our understanding of the universe hits a wall. Everything we know about physics is built on the assumption that space is smooth and continuous, like a sheet of paper. At the Planck scale, that assumption shatters. This is confirmed territory. Physicists do not debate whether the wall exists. They debate what is on the other side of it. And that question has no answer yet. Before we can even approach that question, we need to understand something more immediate. The man who set this limit in motion had no plan to change physics. He was trying to do something almost boring. The story of how he stumbled onto the most fundamental number in the universe starts with a problem that had nothing to do with the smallest scale of reality. And it happened over 100 years ago in a room far from any particle accelerator. In 1899, Max Planck had one job. He was trying to explain how hot objects glow. Not a glamorous problem. But it was breaking physics. Every calculation at the time predicted that a hot, glowing object a furnace, a heated metal rod, a star, should release infinite energy at high frequencies. When scientists ran the numbers, the math exploded. They called it the ultraviolet catastrophe because the equations fell apart at the ultraviolet end of the light spectrum. Planck fixed it. He introduced a strange idea that energy does not flow in smooth, continuous streams. It comes in tiny packets, discrete chunks. He called them quanta. This was the seed of quantum mechanics, one of the most powerful theories in all of science. But buried inside his fix was something else, something he almost missed. To make his equations work, Planck had to introduce a new constant, a number that nature seemed to be using as a kind of minimum ticket price for energy. Scientists now call it Planck's constant, abbreviated as h-bar in modern notation. It is a real, measurable feature of the universe. Planck noticed something while playing with his constants. If you took three fundamental numbers that any civilization would measure, the speed of light, the gravitational constant, and his new constant, and combined them in the right way, you got a set of natural units, a natural length, a natural mass, a natural time, numbers built from the bones of the universe itself, with no human choice involved. Any alien species, on any planet, in any galaxy, running the same physics would calculate the exact same values. He published this in 1890. Physicists appreciated the elegance. Nobody panicked. Nobody declared that physics had a hard flaw. Planck himself described the Planck length as a mathematical curiosity, a clean unit. Nothing more. He moved on. That was the mistake. Or rather, that was the thing nobody caught for decades, because buried in that natural length was a physical limit. Planck had calculated the exact distance below which the laws of physics stopped producing sensible answers. He had drawn the line at the bottom of the universe, without realizing he had drawn any line at all. Here is the striking part. Planck was not a reckless thinker. He was famously cautious. He resisted his own quantum theory for years, trying to find a way to explain the data without breaking classical physics. He did not like radical conclusions, and yet his most radical discovery slipped through without him noticing it. The number sat in plain sight for 60 years. Then, in the late 1950s, a physicist named C. Alden Mead started asking a different kind of question. Mead was not trying to build a unified theory of everything. He was asking something far more direct. He wanted to know whether the laws of physics themselves would allow you to measure distances that small, even in principle, even with unlimited energy. The answer he found was so strange that journals refused to print it. For 5 years, editors told him his reasoning was absurd. He revised the paper, he simplified it, he sent it out again and again. What Mead had discovered would reframe the entire meaning of the Planck length. But to understand why his answer was so threatening to mainstream physics, you first need to understand a rule so basic it applies to every measurement ever made. A rule that connects your location in space to your energy. And it is about to become very inconvenient. Every measurement you have ever made, every single one, works the same way. Something has to bounce. When you look at a coin on a table, photons from a light source hit the coin and bounce into your eye. Your eye reads the pattern. Your brain calls it a coin. When a doctor takes an X-ray, high-energy photons pass through your body and hit a detector on the other side. The pattern of shadows tells the doctor where your bones are. When a sonar system on a submarine pings the ocean floor, sound waves travel down, hit something solid, and return. The time delay tells the crew how far down the floor is. The rule is universal. To detect something, you must interact with it. You have to fire something at it, or let something bounce off it. There is no passive observation. There is no way to simply look without touching. At the human scale, this is obvious, and it does not matter much. Photons bouncing off a coin do not move the coin. The measurement does not disturb the thing being measured. Zoom down to the scale of atoms, and this rule becomes a problem. Electrons are so small that the photons used to locate them actually kick them. The act of measuring changes the position and speed of the electron. This is the beginning of a famous principle in physics, the Heisenberg uncertainty principle. But we will get into that fully in the next chapter. For now, the important part is this. To measure something smaller, you need a probe with a shorter wavelength. Shorter wavelength means higher frequency. Higher frequency means more energy packed into each particle of that probe. Think of it like trying to find a tiny pebble on the bottom of a pool by throwing balls into the water. If your ball is bigger than the pebble, the ball just rolls over it and you miss it entirely. You need a ball smaller than the pebble to get an accurate bounce. The smaller the target, the smaller your probe needs to be, and smaller probes carry more energy. This is confirmed physics. It is the same reason the Large Hadron Collider, which is a machine that fires particles at each other to probe the structure of matter, is 17 miles around and uses enough electricity to power a small city. To see smaller structure, you need more energy. More energy means a bigger machine. This has been the story of particle physics for a century. Now apply this to the Planck length. The Planck length is roughly 1.6 times 10 to the negative 35 meters. To build a probe with a wavelength that short, you would need to concentrate an almost incomprehensible amount of energy into a single particle. Scientists have calculated the exact figure. It works out to about 1.2 times 10 to the 19th power in units called giga-electron-volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches about 14,000 giga-electron-volts at its peak. The Planck energy is about 1,000 trillion times larger than that. That gap alone sounds like an engineering problem. Build a bigger collider. Get more energy. Simple, except the energy required does not just produce a sharper probe. At that scale, energy stops being just energy. It starts becoming something else entirely, something that actively destroys the measurement before any information can come back. That transformation is the next piece of this puzzle. And it starts with a principle so strange that even Einstein spent years trying to disprove it. Werner Heisenberg was 25 years old when he broke reality. He was sick with hay fever in 1925, recovering on a small island off the coast of Germany. Away from pollen and people, he had nothing to do but think. And what he thought about was a problem that had been bothering physicists for years. Why did electrons behave so strangely when scientists tried to pin down exactly where they were? What he worked out on that island is now one of the most confirmed, tested, and strange results in all of physics: the uncertainty principle. Here is what it says. In plain terms, there are pairs of properties in nature that you cannot measure both of at the same time with perfect accuracy. The more precisely you measure one, the less precisely you can know the other. The most famous pair is position and momentum. Position is where something is. Momentum is how fast it is moving and in what direction. If you pin down a particle's position exactly, if you nail it to a perfect point, its momentum becomes completely undefined. The particle could be moving at almost any speed in almost any direction. If you pin down its momentum perfectly, its position smears out across a wide range. You cannot win both at once. This is not a failure of instruments. This is not a limitation of technology. This is a feature of reality itself. The universe genuinely does not allow both values to be precise at the same time. Now connect this to measurement. To locate a particle at a very precise position, you need to hit it with a probe that has a very short wavelength. A short wavelength probe carries very high momentum. When it hits the particle, it transfers a large and uncontrollable kick to the particle's momentum. The more precisely you locate it, the harder you kick it. At normal scales, this is irrelevant. Pinpointing a marble to a fraction of an inch does not require a kick that moves the marble anywhere measurable. But keep shrinking the target. As the target gets smaller, the required probe gets shorter, the energy gets higher, and the kick gets stronger. By the time you are trying to locate something at the Planck scale, the precision required means the probe must carry momentum so enormous that the particle being measured gets an infinite kick. Its momentum becomes completely undefined. Its energy becomes so uncertain that it could be anything. This is the point where the uncertainty principle stops being an inconvenience and starts becoming a physical wall. The more precisely you try to define a location at the Planck scale, the more violently the energy of your measurement spikes. And that spike of energy does something no one expected. The first time it was calculated. It bends space, energy curves space-time. That is confirmed by general relativity, tested 1,000 times, and never failed. A probe carrying Planck scale energy does not just kick the particle, it warps the space around the measurement. And if you push the energy high enough, and at the Planck scale you must, that warping does something final. What happens next is the point where quantum mechanics and gravity collide for the first time, and the result makes measurement completely impossible. The machine does not fail. Space itself fails. 17 miles, that is the circumference of the tunnel buried 300 feet beneath the French-Swiss border, near Geneva. Inside that tunnel, the Large Hadron Collider fires two beams of protons in opposite directions at speeds so close to the speed of light that each proton completes the full 17-mile loop over 11,000 times per second. When those beams collide, the collision releases energy concentrated into a space smaller than a proton. The detectors surrounding the collision point are the size of apartment buildings, filled with millions of sensors designed to capture every particle that flies out from that point. Thousands of scientists across dozens of countries built this machine over decades. It is the most complex scientific instrument ever constructed, and it cannot get even close to what we need. The Large Hadron Collider reaches a peak collision energy of about 14,000 giga-electron volts. That sounds enormous, and for human purposes, it is. It produced the Higgs boson, confirmed the final missing piece of the standard model of particle physics, and has rewritten textbooks across the world. The energy required to probe the Planck length is roughly 1,000 trillion times higher. To be more concrete, if you stacked the energy output of the Large Hadron Collider the way you stack coins, you would need a stack 1,000 trillion coins tall just to reach the bottom rung of what you need. The machine in Geneva barely registers against that requirement. Some physicists have estimated that a particle accelerator powerful enough to directly test the Planck scale would need to be roughly the same diameter as our entire galaxy. The Milky Way is about 100,000 light-years across. 1 light-year is about 6 trillion miles. The machine would need to be 600 quadrillion miles wide. That number is so far beyond anything buildable that it stops feeling like an engineering challenge and starts feeling like a law of nature, saying no. But here is what most people miss. The energy problem is not the real wall. Scientists have gotten creative with energy problems before. The real wall is what happens to that energy once you concentrate it into a space that small. The Large Hadron Collider's collisions are already releasing energy in a tiny volume. They produce particles, and then those particles fly apart. Fine. At the Planck scale, something different happens. The energy does not fly apart. The energy cannot fly apart. The space around the energy has been warped so severely that it collapses inward. The measurement does not just fail, the measurement destroys the location you were trying to measure. Understanding why requires going back to the most famous equation in physics, the one Albert Einstein wrote while trying to connect mass and energy. Most people know the formula. Almost nobody knows what it implies when you push it to its absolute limit. That implication is the next step down, and it is the point where the physics stops being abstract and starts being violent. Albert Einstein published his special theory of relativity in 1905. Buried at the end, almost as an afterthought, was a short paper containing one of the most famous equations ever written. Energy equals mass times the speed of light squared. Most people learn this equation as a fact about bombs and nuclear reactors, but a tiny amount of mass can release enormous energy. That part is true, but the equation works both ways, and the reverse direction is what matters here. Energy and mass are the same thing in different forms. Concentrate enough energy into a small enough space, and it behaves exactly like mass. It curves space-time, it pulls other things toward it gravitationally. It generates a gravitational field. This is not a theory waiting to be confirmed. This is confirmed physics tested in particle accelerators around the world every day. When two protons collide in the Large Hadron Collider with enough energy, that energy creates new particles with real mass. That did not exist a fraction of a second before. Energy becoming mass, live, in a detector. Now scale this up to the energy required to probe the Planck length. The energy needed to build a probe with a wavelength equal to the Planck length is equivalent to a mass of roughly 2 × 10⁸ kilograms. That is about the mass of a flea egg. But that mass, that amount of energy, would be packed into a volume so small that a proton looks like a planet next to it. That concentration of mass in that volume does one thing. Gravity takes over. General relativity, confirmed by over a century of experiments from Mercury's orbit to gravitational wave detectors, tells us that mass curves space. Enough mass in a small enough space curves space so severely that nothing can escape. The escape velocity, the speed needed to get away from that gravitational pull, exceeds the speed of light. When that happens, you have a black hole. This is the trap. To measure the Planck length, you need a probe with enough energy to be equivalent to a flea egg's mass, concentrated into a space far smaller than a proton. The moment you do that, you have crossed the threshold for black hole formation. The measurement tool does not malfunction. The space it was trying to examine collapses into a singularity before any data can return. The probe fires. A microscopic black hole forms. The measurement disappears inside it forever. And here is the part that should make your head spin. The energy inside that black hole does not make the measurement sharper. Adding more energy at this point makes the black hole larger, which makes the resolution worse. Your more powerful microscope is a blinder microscope. The harder you push, the less you see. That backward relationship, more power, less information, breaks every intuition built from human scale experience. And it means the barrier at the Planck scale is unlike any engineering barrier ever faced. You cannot build your way past it. You cannot fund your way past it. Physics itself is the obstacle. What forms in that collapsed space is the next part of the story. And what forms there is something the universe uses to hide information permanently. Most people picture a black hole as something enormous, a dead star 100 times the mass of the Sun, collapsed to a point, swallowing everything nearby. The ones photographed by telescopes are billions of times the mass of the Sun, sitting at the centers of galaxies, pulling in stars and gas across distances measured in light years. Size is irrelevant. What defines a black hole is density and the relationship between mass and the volume it occupies. If you compressed Earth, all of it, every ocean and mountain and molten core, down to a sphere about the size of a marble, it would become a black hole. The mass is the same, only the volume changes. And when the volume gets small enough relative to the mass, gravity wins completely. Every object has what physicists call a Schwarzschild radius, the size it would need to be compressed to in order to become a black hole. For a human being, that radius is roughly 10 to the negative 23 inches. For the Sun, it is about 2 miles. For a proton, it is unimaginably small. These thresholds exist for all matter. Now return to the Planck scale measurement. The probe carrying Planck scale energy carries the mass equivalent of a flea egg. The Schwarzschild radius for that amount of mass, compressed to the Planck volume, is exactly the Planck length. This is the confirmation that seals the trap. At the Planck scale, the energy required to make the measurement and the mass required to form a black hole arrive at the same address at the same time. The measurement and the collapse are the same event. The black hole forms instantly. It forms at the moment of the measurement attempt, and it forms at a size equal to the very distance you were trying to measure. Physicists describe this as the gravitational paradox of Planck scale measurement. General relativity, which normally operates at the large scale, reaches down all the way to the smallest scale and slams a door. The two great theories of physics, quantum mechanics and general relativity, normally avoid each other by operating at different size scales. Quantum mechanics handles the tiny, relativity handles the large. At the Planck length, they are forced to occupy the same space, and when they collide, the result is a black hole that swallows the measurement. Here is something that makes this stranger. The black hole formed is the smallest black hole that physics permits. Its event horizon, the boundary of no return, is exactly 1 Planck length wide. The thing you are trying to measure has turned into the precise object that hides its own measurement. This feels like the universe protecting a secret. That framing is poetic rather than scientific, but the outcome is identical. Whatever exists at the Planck scale is permanently shielded from direct observation, locked behind an event horizon that forms the instant you try to look. What exactly an event horizon does to information, why nothing that crosses it can ever be retrieved, is the next layer down, and understanding it will explain why the measurement does not just fail. It fails in the most complete and permanent way physics knows. An event horizon is a point of no return. Cross it moving inward, and you cannot come back out. Even light, the fastest thing in the universe, cannot climb back out once it has crossed this boundary. This is not a barrier in the physical sense. There is no wall, no surface, no sign. An event horizon is a location in space where the escape velocity, the speed needed to pull away from gravity, exceeds the speed of light. Since nothing can travel faster than light, anything crossing that line is permanently trapped inside. Every measurement instrument ever built relies on a return signal. Sonar sends sound waves and waits for the echo. A microscope sends photons and reads the ones that bounce back. A particle collider fires particles and reads the debris that flies outward. Every detection method in physics depends on something coming back to a detector. An event horizon eliminates that return completely. Any particle, any photon, any signal fired into the Planck scale black hole formed during a measurement attempt is gone. It crosses the event horizon and never comes back. The detector registers nothing. The instrument reports nothing. The measurement returns no data. This is confirmed by everything physicists know about black holes. The event horizon is the universe's most efficient information blocker. Here is the piece that makes it worse. You might expect that firing a stronger signal, more energy, more particles, would push information back out past the horizon. The opposite happens. Adding more energy to the measurement attempt increases the mass of the forming black hole, which increases the size of its event horizon, which captures more of the return signal. A stronger probe produces a larger black hole that hides more information. The machine that physicists imagined, an instrument so powerful it could probe the Planck length, would, in practice, create a progressively larger black hole with every increase in power. The resolution would get worse, not better. The instrument would be shrinking its own ability to see. This is the measurement paradox confirmed by theoretical physics. It was first rigorously described by C. Alden Mead in 1964, though journals refused to print his paper for years because the conclusion seemed too strange. Mead showed mathematically that gravity enters the uncertainty equation at the Planck scale and makes precise measurement impossible in principle, regardless of technology. The event horizon is final. Once data crosses it, quantum mechanics itself, the theory of the very small, says that information cannot be destroyed, but also cannot escape a black hole. This creates a paradox that the best minds in physics have spent decades trying to resolve, and have not solved yet. What is happening inside that horizon, at the very floor of reality, is something stranger than any science fiction scenario. John Wheeler, one of the physicists who shaped modern understanding of black holes, gave it a name in the 1950s. He called it quantum foam, and what he described changed how physicists think about space itself. Physics has many counterintuitive results. Quantum mechanics tells us particles can be in two places at once. Relativity tells us time moves slower near a massive object. These ideas feel strange, but you can build some mental picture around them. The paradox at the Planck scale is different. It runs directly against the assumption that more effort produces better results. Every tool humans have ever built follows the same logic. A sharper knife cuts better. A more powerful telescope sees farther. A more energetic probe sees smaller. The entire history of science is built on the idea that improving the instrument improves the measurement. At the Planck scale, this breaks completely. To measure a smaller distance, you need a probe with more energy. Confirmed. More energy means more mass equivalent packed into a smaller space. Confirmed. More mass in a smaller space means a larger Schwarzschild radius. Confirmed. A larger Schwarzschild radius means a larger event horizon. Confirmed. A larger event horizon swallows more of the return signal. Confirmed. Put all of those confirmed steps together and you get a result that should stop you cold. Increasing the energy of your probe increases the size of the black hole that forms, which increases the minimum distance your measurement can resolve. The more power you use, the blinder the instrument becomes. Physicists call this the inverse relationship between probe energy and measurement resolution at the Planck scale. At every other scale in physics, these two move together. More energy, sharper resolution. At the Planck scale, they flip. More energy, coarser resolution. Picture trying to read fine print with a magnifying glass. Normally, a stronger lens brings the print into focus. Now imagine a magnifying glass where turning up the power causes the print to smear wider, where maximum power shows you nothing but a blank blur. That is the situation at the Planck scale, confirmed by the mathematics of both quantum mechanics and general relativity combined. This paradox has an exact mathematical form, called the generalized uncertainty principle. It is an extension of Heisenberg's original uncertainty equation that adds a gravitational correction term. The original principle sets a minimum uncertainty in position based on quantum mechanics alone. The generalized version adds a second uncertainty floor imposed by gravity. At the Planck scale, gravity's correction term dominates. The result is a hard lower limit on measurable distance. The generalized uncertainty principle predicts that the minimum measurable length is the Planck length itself. You cannot do better. You cannot approach it asymptotically. You cannot chip away at it with better engineering. The floor is absolute. This was not intuitive. Physicists resisted it. When C. Alden Mead first presented his version of this argument in the early 1960s, multiple journals rejected the paper outright. Reviewers called it too speculative. One editor reportedly told Mead the argument was interesting, but the conclusions could not be taken seriously. Mead spent 5 years revising, simplifying, and resubmitting. The story of how he eventually got his result into print is one of the stranger episodes in the history of modern physics, and what he had to do to get reviewers to take his math seriously is either clever or absurd, depending on how you look at it. In 1958, a young physicist named C. Alden Mead was working through the implications of combining quantum mechanics and gravity. He was not looking for fame. He was trying to answer a specific question that had been bothering him. Could you, even in principle, measure a distance smaller than the Planck length? His approach was straightforward. He would take the known rules of quantum mechanics, apply them to a measurement device, add in gravity as described by general relativity, and see what came out. What came out was a wall. His math showed that gravity enters the Heisenberg uncertainty principle at the Planck scale and adds a new term, a gravitational contribution to position uncertainty that grows with the probe energy. The higher the energy, the larger this gravitational term. and therefore the larger the uncertainty in position. Below the Planck length, the gravitational uncertainty overwhelms any quantum precision you try to achieve. He wrote this up. He submitted it to Physical Review, one of the most respected physics journals in the world. It was rejected. He revised. He submitted to another journal. Rejected again. The pattern repeated for 5 years. Editors and reviewers told him his reasoning was unconventional, that the conclusion was too dramatic, that the assumptions were unproven. Mead kept at it. He believed his math was correct, and his math was correct. The problem was that in 1959, the combination of quantum mechanics and gravity was considered a fringe interest. Most physicists treated the two theories as separate tools that worked in separate domains. The idea that they would collide at the Planck scale and produce a physical measurement limit struck many reviewers as a solution to a problem nobody thought was real. By 1964, Mead had simplified his paper down to its bare essentials. He stripped out every part that gave reviewers an excuse to argue. He reduced the argument to its most unassailable mathematical core. Physical Review letters finally published it. The paper landed quietly. Most physicists barely noticed. The concept of a fundamental measurement limit was still considered fringe territory, and Mead was not famous enough to force people to pay attention. Decades passed. Then, as quantum gravity became a serious field of research in the 1980s and 90s, physicists working on string theory and loop quantum gravity began arriving at the same conclusion through completely different mathematical paths. They started looking back at the literature and found Mead's paper sitting there, decades earlier, with the answer already written. Today, his work is cited as a foundational result in quantum gravity. He proved the wall existed before most physicists believed the wall was a real thing worth looking for. But Mead's paper described the limit in terms of measurement. It said you cannot measure below the Planck scale. It did not fully describe what that scale looks like, what the texture of space itself becomes when you reach the floor. That description came from a different physicist working in a different way, and what he imagined was something no one had pictured before. The story of how C. Eldon Mead finally got his paper published is a lesson in the sociology of science, and it is slightly absurd. By the early 1960s, Mead had been trying for years to get a journal to accept his result, that combining quantum mechanics and gravity produces a fundamental length below which measurement becomes impossible. The physics was sound. The math was correct. The problem was the conclusion. Every time reviewers encountered the final result, they rejected the paper on the grounds that it was too speculative or relied on unproven assumptions about quantum gravity. Mead's solution was to strip the paper down until there was almost nothing left for reviewers to grab onto. He removed every claim that required a deep commitment to quantum gravity as a framework. He reduced the argument to the most minimal possible set of assumptions, ones that virtually every physicist already accepted individually. He did not claim to describe what happens at the Planck scale. He only claimed to show that quantum mechanics and gravity together impose a lower limit on measurement precision. The second version of the paper read almost like a calculation exercise. Here are the rules, here is the math, here is the result. No dramatic framing, no sweeping conclusions, just the math, stated as plainly as possible. Physical Review letters accepted it in 1964. The irony is significant. The stripped-down version was actually harder for most readers to understand, because all the physical intuition had been removed to avoid giving reviewers an argument. The paper contained the most important result, wrapped in the most minimal presentation. What happened next was silence. For years, the paper sat in the literature, occasionally cited, occasionally discussed in small circles, but never becoming a landmark. Mead moved on to other research. The result did not immediately reshape the field, because the field was not yet ready to take quantum gravity seriously as a research program. The rehabilitation of Mead's result happened gradually. Through the 1980s and 90s, as physicists working on string theory and loop quantum gravity independently rediscovered the same minimum length from completely different starting points. When researchers went back through the literature, Mead's paper was already there. He had been right, and nobody had paid enough attention to realize it. His case is a clear example of a result that arrived too early for its field. The conclusion was correct. The math was valid. The resistance came from the fact that the question itself, what happens when you try to merge quantum mechanics and gravity, was not yet considered worth asking seriously. Mead's stripped-down paper described the measurement limit in purely mathematical terms. It said, "The wall exists." It did not say what the wall looks like from the inside. That vision, the actual texture of space at the Planck scale, came from a physicist who was famous for asking exactly that kind of visual question. A man who imagined black holes before black holes had a name, and his picture of the Planck scale was so strange it became its own scientific concept, still debated today. John Wheeler was the kind of physicist who named things. He coined the term black hole. He popularized the term wormhole. He gave physicists a language for ideas so strange that existing words could not hold them. In the 1950s, he turned his attention to the Planck scale, and he came up with a name for what he found there. Wheeler asked a simple question. If space is smooth and continuous at the scales we observe, what is it doing at scales we cannot observe? Specifically at the Planck scale, where quantum mechanics and gravity are both operating at full strength simultaneously. His answer was quantum foam. Here is the picture. At the scales of everyday life, space looks smooth, flat, stable, like a calm ocean surface viewed from far above. Zoom in, and the surface still looks smooth. Zoom in further, to the scale of atoms, and space still behaves like a continuous fabric. Now zoom all the way down to the Planck scale. Wheeler's argument was that at this distance, the Heisenberg uncertainty principle applied to space and time themselves. Space and time are not made of some fixed substance. They are dynamic. They fluctuate. Quantum mechanics says that any property measured with extreme precision at tiny scales will have corresponding uncertainty in related properties. Applied to the geometry of space, this means the shape of space itself, its curvature, its topology, should fluctuate wildly at the Planck scale. The result would look nothing like a smooth surface. It would look like foam, like the chaotic, constantly changing surface of boiling water viewed so closely that each individual bubble is visible, popping in and out of existence faster than any measurement can track. Tiny regions of curved space forming, collapsing, and reforming in a churning texture. Virtual black holes blinking in and out of existence. Wormhole-like connections forming and dissolving. Wheeler called this quantum foam in the 1950s. He described it as the fundamental texture of space, the pixel grid, if the universe has one. This idea is still theoretical. No experiment has directly confirmed quantum foam. The Planck scale remains completely beyond the reach of direct measurement, for all the reasons described in the previous chapters. But quantum foam is consistent with everything known about quantum mechanics and general relativity, and multiple theoretical frameworks independently arrive at some version of this picture. The image is worth sitting with. The space you are occupying right now, at the scale of atoms, looks smooth. At the Planck scale, that same space would be a storm. Geometry itself writhing, topology snapping. Space not as a fixed stage on which events happen, but as an active, seething participant in its own chaos. And here is the piece that follows directly from Wheeler's foam. If space itself is turbulent at the Planck scale, the concepts we use to describe location, up, down, left, right, before, after, become meaningless. Position requires a fixed reference. A direction requires a stable geometry. At the Planck scale, geometry is the thing that is failing. What that means for the basic structure of space and time is stranger than quantum foam itself, and it is where the physical picture gets genuinely disturbing. Every direction you have ever moved has relied on a fixed background. Up means away from the center of the Earth. North means toward a magnetic pole. Before means earlier in a sequence of events. After means later. These are not just words, they are descriptions of a geometry that stays stable while things happen inside it. At the Planck scale, that geometry stops being stable. Here is what this means in practice. At normal scales, you can mark a location in space with coordinates. You can say this point is here, and that point is 3 feet away in that direction. This works because the fabric of space between those 2 points is smooth, continuous, and well-behaved. The distance between them is a definite number. At the Planck scale, quantum foam means the geometry between any 2 points is wildly fluctuating. The distance between them is not a single definite value. It is a probability distribution, a smear of possible values, all happening simultaneously, with no fixed answer. You cannot say a point is here, because here is not a stable location. Space is not providing a reliable background for the measurement. This is more than just a measurement problem. It challenges the concept of location itself. If 2 events happen at the Planck scale, 2 virtual particles appearing, 2 quantum fluctuations firing, you cannot reliably say whether one happened before or after the other. Time, which normally runs in a fixed sequence, also fluctuates at this scale. Before and after become statistical tendencies, not guaranteed facts. This is an unknown territory. Physicists believe this is what the Planck scale looks like based on theoretical arguments, but no experiment has confirmed the picture. John Wheeler's quantum foam captures the chaos, but it does not resolve it. The deeper problem is that quantum mechanics and general relativity make incompatible assumptions about space and time. Quantum mechanics treats space and time as a fixed stage. General relativity treats space and time as dynamic and curved. At the Planck scale, neither assumption holds, and no theory yet tells us what replaces them. The language of physics, coordinates, distances, durations, is built on the assumption of a stable space-time. At the Planck scale, that assumption fails. Physicists are left trying to describe a reality that their mathematical language was not designed to capture. Some have compared it to trying to describe color to someone who has only ever seen in black and white. The concepts just do not map. A new framework is needed, and nobody has built it yet. This breakdown of direction and time is confirmed in the sense that current mathematics cannot handle the Planck scale without producing nonsense. It is unknown in the sense that we do not know what the correct description looks like. The absence is real. The replacement is missing. And the deeper you push into this problem, the more it starts to look less like a gap in knowledge and more like a fundamental feature of reality, a pixel limit on the universe. The idea that space is not infinitely divisible, that it has a grain, like a photograph when you zoom in far enough, has become one of the most serious proposals in modern physics. And it comes with 2 very different answers about what that grain looks like. Every digital photograph is made of pixels. Zoom in on any image, and eventually you hit the grid. The picture breaks down into squares of solid color. You cannot find details smaller than a pixel because the pixel is the smallest unit of information the image contains. The resolution is finite. Physicists have been asking whether the universe works the same way. The Planck length sits at the center of this question. If space is continuous, if you can always divide a distance in half no matter how small, then the Planck length is just a measurement limit imposed by practical physics. The distance below it exists. We simply cannot observe it. If space is quantized, if it comes in discrete chunks that cannot be subdivided, then the Planck length marks the actual grain of the universe. Below it, there is no smaller distance. Space does not exist at that resolution. These 2 possibilities have completely different implications. A continuous space with a measurement limit means reality goes deeper than we can reach. There could be structure below the Planck scale. We are simply blind to it. The universe has more detail than we can ever access. A quantized space with a true pixel limit means reality ends at the Planck scale. Below it, the question, what is there, has no answer because there is no there. Space simply does not extend further. Current physics cannot distinguish between these two cases. The measurement barrier prevents direct access, and both pictures are mathematically consistent with what we can observe. This is a genuinely open question in physics. Some physicists find the quantized picture more satisfying. It eliminates certain mathematical infinities that plague quantum field theory. When you integrate over all possible scales in many physics equations, you get infinite results that need to be manually removed, a process called renormalization. If space is quantized and stops at the Planck scale, many of these infinities disappear naturally. The math becomes cleaner. Others reject the pixel picture because it breaks one of the most successful symmetries in physics, Lorentz symmetry, which is the mathematical backbone of relativity. If space is quantized like a grid, then the grid has a preferred orientation, which would mean different observers moving at different speeds would measure different minimum lengths. Experiments have searched for this effect and found nothing, which is a serious constraint on pixelated space models. The question is open, the experiments are running, and the two leading candidates for a theory of quantum gravity, string theory and loop quantum gravity, have completely different answers to whether the universe has a pixel limit. Their disagreement is fundamental, and both answers are strange enough to deserve their own chapter. String theory starts with a single claim: the fundamental building blocks of the universe are strings. Every particle you have ever heard of, electrons, quarks, photons, everything in the standard model of particle physics, is, according to string theory, the same kind of object, a tiny vibrating loop or strand of energy. The different particles are the same string vibrating at different frequencies, the way the same guitar string can produce different notes depending on how it is plucked. The size of these strings matters enormously here. String theory predicts that the fundamental strings are approximately 1 Planck length long. This is not a coincidence, it is a consequence of the mathematics. When physicists work out the equations of string theory and ask what size the strings must be to produce the particles we observe, the answer comes back as the Planck length. The theory does not take the Planck length as an input and produce strings. The strings come out at that size naturally from the math. What this means for the pixel question is direct. If the smallest things in the universe are strings 1 Planck length long, then no physical object can be smaller than a Planck length. You cannot subdivide a string. You cannot probe inside it with another string, because the probe is the same size as the target. The Planck length is the fundamental grain of string theory, not just a measurement limit but a structural limit on what exists. String theory also provides a different answer to the measurement problem. In normal quantum mechanics, probing smaller distances requires shorter wavelength probes, carrying higher energy. This is the relationship that leads to the black hole problem. String theory modifies this relationship. When the wavelength of a string probe shrinks below the Planck length, something surprising happens. The string starts behaving as if its wavelength is growing again. Physicists call this T-duality. It is a symmetry in string theory that makes a string with a very short wavelength mathematically equivalent to a string with a very long wavelength. The universe looks the same below the Planck scale as it does above it, not because the physics is the same, but because the two regimes are mathematically dual to each other. The Planck length is the center of the mirror. This is a remarkable claim. String theory predicts that the universe does not get smaller below the Planck length. The concept of distance itself wraps around and starts increasing. Going below the Planck scale is the same as going above it, just described differently. String theory has not been confirmed experimentally. The energy required to directly detect strings is far beyond current technology. In fact, it is Planck energy, the same all encountered in every other approach. The theory is mathematically rich and internally consistent, and it provides the most detailed picture of what the Planck scale looks like, but it remains unverified. Loop quantum gravity offers a completely different picture, and unlike string theory, it does not require extra dimensions or new particles. It works with the ingredients already known, and its answer to the pixel question is blunter, stranger, and somehow even harder to picture. Loop quantum gravity begins with a different question than string theory. String theorists start by asking what particles are made of. Loop quantum gravity theorists ask what space is made of. The answer loop quantum gravity provides is this: space itself is quantized. At the human scale, space looks smooth and continuous. You can move through it in any direction by any amount. There is no grid. There is no minimum step. At the Planck scale, loop quantum gravity says this smoothness is an illusion, a large-scale average that hides a discrete underlying structure. Space, in loop quantum gravity, is made of chunks, discrete units, like atoms of space. Each unit is roughly 1 Planck length in size. You cannot have a piece of space smaller than this. Asking what is between two adjacent chunks is like asking what is between two adjacent integers. There is no between. The chunks are the structure. The technical name for these units involves a mathematical object called a spin network, a web of nodes and connections that encodes the quantum state of space. Each link in the web carries a discrete value of area or volume. Space does not exist continuously between the links. Space is the links. This is a harder idea to hold on to than string theory's vibrating strings. String theory replaces point particles with tiny lines, but keeps space as a continuous background. Loop quantum gravity eliminates the continuous background entirely. Space is the discrete structure, and there is no empty stage behind it. What this means for the Planck length question is direct. Loop quantum gravity does not say the Planck length is a measurement limit. It says the Planck length is the smallest actual piece of space. Below it, there is nothing to measure because there is no space there to measure. The pixel question gets a definitive answer in loop quantum gravity. Yes, the universe has pixels. They are called spin network nodes. They are Planck length sized, and they are not just the limit of our measuring ability. They are the substance of space itself. Loop quantum gravity also makes a specific prediction about the Big Bang. If space is quantized, then the singularity, the infinitely dense point that standard cosmology places at the beginning of the universe, cannot exist. A Planck volume chunk of space cannot be compressed further. So, instead of a singularity, loop quantum gravity predicts a big bounce, a previous contracting universe that reached the Planck density and rebounded outward. This prediction is testable in principle through signatures it might leave in the cosmic microwave background radiation, the faint glow of heat left over from the early universe. Experiments are looking for these signatures. String theory and loop quantum gravity both arrive at the Planck length as the fundamental scale. They agree on the address, but disagree completely on what lives there. One says vibrating strings, the other says chunks of space. Both cannot be right in their current form. And here is what is strange about this disagreement. The conflict between these two theories goes deeper than competing models. They disagree about the nature of space itself. One keeps space as a backdrop, the other makes space the main character. That disagreement sits at the heart of the biggest unsolved problem in physics, and the tools that might resolve it have their origins in a set of 3 numbers that any civilization in the universe would calculate the same way. Every measurement system humans have invented is based on human choices. The meter was originally defined as 1/10,000,000th of the distance from the North Pole to the equator. The pound was based on the weight of a specific physical object, stored in a vault in London. The second was originally defined by dividing the day into fixed fractions. These choices are arbitrary. A civilization on another planet would never arrive at the same numbers unless they happened to make the same arbitrary decisions. The Planck length is different. It is built from constants that are features of the universe itself. 3 numbers go into the formula. First, the speed of light, the maximum speed at which information can travel in this universe. This is not a property of light specifically. It is a property of space and time. The speed of light is the same for every observer, regardless of their motion, and it has the same value everywhere in the universe. Second, The gravitational constant, the number that describes how strongly mass and energy curve space. This constant appears in every gravitational calculation from the orbit of the Moon to the behavior of black holes. It is the same everywhere in the observable universe. Third, the reduced Planck constant, the number that sets the scale of quantum effects. It appears in the uncertainty principle, in the energy of photons, in the behavior of electrons in atoms. It is the fundamental quantum of action in the universe. Combine these three constants in the right way, and you get the Planck length. The formula produces the same number no matter who runs it, or where they run it. A civilization a billion light years away, using a completely different language and a completely different measurement history, running the same calculation, would land on the exact same physical distance. Max Planck recognized this in 1899. He called it a natural system of units. He said it was the only system that any civilization in the universe would independently calculate the same way. He described the Planck units as meaningful across all of time and space, not just for humans. He was right about the universality. He missed the fact that the length was also a physical limit. The three constants are linked in a specific way that makes the Planck length special. The speed of light connects space and time. The gravitational constant connects mass and geometry. The reduced Planck constant connects energy and position uncertainty. The Planck length is the exact distance where all three connections tighten simultaneously and produce a contradiction, a point where geometry, gravity, and quantum uncertainty all demand the same address, and none of them can be satisfied at the same time without a black hole forming. This is why the Planck length is the limit. It is the address where three independent features of the universe collide at once. Any universe with the same three constants would have the same limit. Any alien civilization measuring those constants would calculate the same wall. And every universe with that wall would have the same question underneath it, the question of what Planck time means. Because the Planck length is not just a distance. Paired with the speed of light, it defines something even stranger. A minimum tick of time, the shortest moment that can exist. And what that means, what it says about whether time is smooth or granular, is the next layer of this story. Time feels continuous. 1 second flows into the next. Moments blend. There is no gap, no jump, no skip. Even when something happens fast, a camera flash, a lightning strike, a blink, time underneath it is still smooth. There is always a shorter moment inside the short one, or so it seems. Planck time is the duration it takes light to travel 1 Planck length. Since the Planck length is the smallest measurable distance, and since light is the fastest thing allowed by the universe, Planck time is the shortest duration that carries any physical meaning. It works out to roughly 5 times 10 to the negative 44 seconds. Written out, that is a decimal point, followed by 43 zeros before the 5. To put that in perspective, 1 second contains more Planck time units than the current age of the universe contains seconds. The universe is about 13.8 billion years old. 1 second contains vastly more Planck moments than that entire span contains seconds. A single heartbeat contains more fundamental ticks of time than there have been seconds since the Big Bang. That scale is almost impossible to hold in your mind. And that is the point. Here is the question that follows directly from this. If the Planck length is the smallest meaningful distance, and Planck time is defined by that distance, then is time quantized? Does it flow continuously, or does it advance in discrete jumps? 1 Planck tick at a time, like frames of a film. This is genuinely unknown. Physicists disagree. General relativity treats time as continuous and smooth. Loop quantum gravity, as described in the last chapter, suggests time may also be quantized into Planck time chunks, the same way it proposes space is chunked into Planck length units. String theory treats time differently again, as part of a higher dimensional structure. Some experiments have been designed to look for signs of quantized time. The logic is this: if time is granular, then photons of different energies traveling across billions of light years should arrive at slightly different times, because high-energy photons interact differently with the quantized grid than low-energy ones. Gamma-ray telescopes have observed high-energy light from distant cosmic explosions and measured the arrival times with extreme precision. So far, no delay has been detected. This constrains but does not rule out quantized time. The absence of a detected delay pushes certain models of quantized spacetime into difficulty, but the experiment has not closed the question. The effect, if it exists, may be smaller than current detectors can resolve. What makes Planck time philosophically alarming is the implication for causality. Cause must come before effect. Before and after must be meaningful. If time has a minimum unit, then two events separated by less than one Planck tick are simultaneous in a physical sense. The universe cannot distinguish their order. Causality at that scale becomes undefined. Two events at the Planck scale could be connected by cause and effect, or they could be genuinely unordered, with no fact of the matter about which came first. The sequence of reality at its finest grain may be statistical rather than absolute. That thought that the order of events is not guaranteed at the smallest scale connects directly to the next piece, because if time and space both lose their structure at the Planck scale, then the energy required to probe that scale does something even stranger to mass. And the number that comes out of that calculation is one of the most unsettling comparisons in all of physics. The Planck mass is the amount of mass whose Schwarzschild radius equals the Planck length. In plain terms, it is the smallest amount of mass that can form a black hole exactly 1 Planck length wide. The number works out to roughly 2 × 10⁻⁸ kilograms. That is about 22 micrograms. Scientists have a more vivid way to picture it. The Planck mass is approximately equal to the mass of a flea egg. A flea egg. That is the mass you would need to concentrate into a volume far smaller than a proton in order to probe the Planck scale. Sit with that comparison. A flea egg is a biological object. You can see one with a magnifying glass. It is real and physical, and small but completely ordinary. Yet the mass of that flea egg, compressed into a space that makes a proton look enormous, represents the absolute minimum threshold for a black hole that erases your measurement. This comparison works as a bridge between human intuition and Planck scale physics. The Planck mass is not large by cosmic standards. It is tiny, but it is enormous by particle physics standards. The most energetic particles ever produced in an accelerator carry energies billions of times smaller than the Planck mass equivalent. The gap between what we can build and what we would need is not a matter of incremental improvement. It is a matter of kind. Here is what makes the Planck mass strange from a different angle. In most of physics, mass and energy concentrate into smaller spaces as you go to higher energies. Particle accelerators produce particles of higher and higher mass, and those particles are more and more compact. The trend should continue. Cram enough energy into a small enough space, and you get a smaller, denser particle. At the Planck scale, this trend reverses. The particle you would need to produce to probe the Planck length has a mass equivalent of 22 micrograms, larger than any fundamental particle by an absurd margin, but its size is the smallest possible. Mass going up, size going down, until the Schwarzschild radius matches the wavelength, and collapse is unavoidable. The Planck mass is the exact crossing point. Below this mass, a particle's quantum wavelength is larger than its Schwarzschild radius, and it behaves like a quantum particle. Above this mass, the Schwarzschild radius exceeds the quantum wavelength, and it behaves like a black hole. The Planck mass is the boundary between quantum objects and gravitational objects. Every fundamental particle you have ever heard of, electrons, quarks, neutrinos, is far below the Planck mass and behaves quantum mechanically. A Planck mass particle would be a black hole. This boundary is sometimes described as the point where quantum mechanics hands off to gravity. Below the Planck mass, quantum mechanics runs the show. At and above it, gravity takes over permanently. And there is a photon implication here that very few people know about. A photon is a particle of light with zero mass, but a photon with enough energy behaves as though it has mass through the mass-energy equivalence. A photon energetic enough to have a wavelength equal to the Planck length would have an energy equivalent to the Planck mass, and that photon would be by definition a black hole. Light itself, at that energy, becomes a black hole. The thing that normally carries information becomes the thing that traps it. Light carries no mass. That is confirmed by every experiment ever run on photons. A photon travels at the speed of light precisely because it has no rest mass. If it had mass, it could never reach that speed. But a photon carries energy, and energy, through Einstein's confirmed equation, is equivalent to mass. A photon with higher energy behaves gravitationally as if it has more mass, even though its rest mass is zero. This is not a theory. Confirmed measurements show that light bends around massive objects because gravity acts on the energy of the photon. Now push the photon's energy up to the Planck scale. A photon with energy equal to the Planck mass equivalent has a wavelength exactly equal to the Planck length. Its Schwarzschild radius, the radius of the black hole its energy would form if concentrated into a point, equals its own wavelength. The gravitational and quantum descriptions of that photon collapse into the same number. At that point, the photon is a black hole. A photon moving at the speed of light, which normally carries information freely across the universe, becomes a self-contained gravitational trap. It cannot deliver its signal, it cannot bounce back data. It is simultaneously the messenger and the prison. This is theoretical, based on the combined application of quantum mechanics and general relativity. But it has a concrete implication. Any probe, any particle, any photon, energetic enough to resolve the Planck scale, becomes a black hole before it can return information. The measurement is always destroyed from the inside. This conclusion converges with everything discussed in the earlier chapters, but from a new angle. The photon case makes the problem feel more immediate. Light, the thing that carries information in every measurement ever made, fails at the Planck scale specifically because it becomes the barrier it was supposed to cross. Some physicists have pointed out that this creates a kind of cosmic irony. The universe uses light to communicate. Every telescope, every detector, every experiment relies on light or something behaving like light. And at the very bottom of reality, the tool breaks permanently. The universe's own communication system becomes the mechanism that enforces the measurement limit. What fills that space below the light barrier is something Wheeler tried to capture with quantum foam, but the foam is not empty. It is not quiet. The space at and below the Planck scale is theorized to be filled with activity, particles appearing and vanishing, energy fluctuating, geometry churning. Physicists have a specific term for the objects that fill this boiling space, and the picture they describe looks less like empty space and more like a storm that was always there, invisible, beneath everything you have ever observed. Empty space is not empty. This is confirmed by experiment. Physicists have measured it. Pull two metal plates very close together in a vacuum, a real vacuum, pumped clean of every particle, and the plates will be pushed together by a measurable force. The vacuum is pushing them. Something in the emptiness is generating pressure. That something is virtual particles. Here is how they work. Heisenberg's uncertainty principle applies to energy and time the same way it applies to position and momentum. If you measure the energy of a region of space over a very short time interval, the uncertainty in the energy reading becomes very large. This means that over extremely short time intervals, energy can appear from nothing, as long as it disappears again before the uncertainty window closes. The universe borrows energy, uses it briefly, and returns it. The pairs of particles that appear and disappear are called virtual particles. They are not hypothetical. Their effects are measured in laboratories. The pressure between the metal plates, called the Casimir effect, is a direct consequence of virtual particle activity in the vacuum between the plates. At normal scales, virtual particle activity is a small correction to calculations. Quantum field theory accounts for it with precise mathematical tools, and the results match measurements to extraordinary accuracy. The vacuum hums quietly in the background. At the Planck scale, the activity becomes extreme. The shorter the time interval, the larger the allowed energy fluctuation. At Planck time, the smallest time unit, the energy uncertainty becomes enormous. Virtual particles can appear with energies approaching the Planck scale. These are particles energetic enough to form microscopic black holes, appear and disappear, all within a single Planck tick. Wheeler's quantum foam is, in physical terms, this process happening everywhere simultaneously at the Planck scale. Space, at its finest grain, is a boiling storm of virtual particles flashing in and out of existence. Each one a brief fluctuation in the energy of the vacuum, each one potentially a microscopic black hole forming and evaporating before any information can be extracted. This connects to a result from the physicist Stephen Hawking. Hawking showed theoretically that black holes are not completely dark. Virtual particle pairs appearing near a black hole's event horizon can be split. One particle falls in, one escapes. The escaping particle carries energy away. The black hole slowly loses mass and eventually evaporates. At the Planck scale, this process is happening constantly for the smallest possible black holes. The virtual black holes of quantum foam form and evaporate in single Planck time ticks. The space you are sitting in right now contains this storm at every point, at a scale too small for any instrument to reach. The storm has consequences. It means the vacuum is not a neutral background. It is a dynamic participant in physics. And when two of the greatest theories of physics try to describe this same space, they produce answers that directly contradict each other. That contradiction has never been resolved. And understanding why it exists, why quantum mechanics and general relativity cannot both be right at the Planck scale, is the clearest way to see what is actually broken at the bottom of physics. Two theories run the universe. That is the problem. Quantum mechanics governs the very small, atoms, electrons, photons, the forces between particles. It has been tested to extraordinary precision. Its predictions match experiments to more than 10 decimal places. No theory in the history of science has been confirmed more thoroughly. General relativity governs the large. Gravity, the geometry of space, the behavior of massive objects. It predicted gravitational waves decades before they were detected. It explained the precise precession of Mercury's orbit, which Newtonian gravity could not. It predicted black holes before any were observed. Every test has confirmed it. Both theories are right, both are confirmed, both are the best descriptions of their domains that humanity has ever produced, and they cannot both be right at the same time. Here is the core conflict. Quantum mechanics describes a universe built on probability. Particles do not have definite positions. They exist in superpositions, a smear of possible states, until measured. The universe at the quantum scale is fundamentally uncertain, fundamentally discrete in its energy levels, and fundamentally probabilistic in its outcomes. General relativity describes a universe built on smooth geometry. Space-time is a continuous fabric. Objects follow smooth curves through that fabric. Gravity is the curvature of that fabric, caused by mass and energy. The theory requires space to be perfectly smooth and continuous to work. Quantum mechanics says space is smooth. Both cannot be simultaneously true at the same scale. At the human scale, this does not matter. Quantum effects are negligible when calculating the orbit of the moon. Gravitational curvature is negligible when calculating the behavior of an electron in an atom. The theories operate in separate domains and never have to face each other directly. At the Planck scale, they cannot avoid each other. The gravitational curvature of a Planck scale object is enormous. It produces black holes during measurements. The quantum uncertainty of a Planck scale object is total. Position and energy are fundamentally smeared. Both effects are happening at full strength simultaneously, and no mathematical framework currently handles both at once without producing infinities or nonsense. Physicists call the missing theory quantum gravity. It does not exist yet. String theory is a candidate. Loop quantum gravity is a candidate. Several other approaches are in development. None has been confirmed by experiment. None has produced a complete, consistent mathematical framework that reduces to quantum mechanics at small scales and general relativity at large scales. The absence of quantum gravity is the single biggest gap in theoretical physics. Every other piece of the standard model is connected. Electromagnetism, the weak force, and the strong nuclear force are unified in the standard model of particle physics. Gravity stands completely outside. At the Planck scale, where gravity and quantum mechanics are both running at maximum strength, the missing theory is most urgently needed and most obviously absent. This gap in physics is not a small technical detail. It is a sign that something fundamental is wrong or missing in the current picture of reality. The Planck scale is where that wrongness or incompleteness becomes undeniable, and building a machine that could directly test the Planck scale would at least tell us what answers to look for, even if that machine would have to be the largest structure ever imagined. The Large Hadron Collider is 17 miles around. It took decades to build, cost roughly $10 billion, and required contributions from over 100 countries. It is the most ambitious scientific machine in history, and it reaches energies about 1,000 trillion times smaller than what the Planck scale requires. Physicists have estimated the size of an accelerator that could directly test the Planck energy. The calculation is straightforward in principle. Bigger ring, stronger magnets, higher energy. Run the numbers forward from the Large Hadron Collider's 17 miles and its 14,000 giga-electron-volt maximum, and scale up to Planck energy. The result is a ring roughly 100,000 light-years in diameter. That is approximately the diameter of the Milky Way galaxy. The accelerator would need to be as wide as the entire galaxy we live in. 1 light-year is about 6 trillion miles. 100,000 light-years is 600 quadrillion miles. The ring would span from one edge of the galaxy to the other, using the gravitational and magnetic infrastructure of billions of star systems, powered by energy sources we cannot yet imagine. This is not a proposal. Physicists state this number to make the gap concrete. Direct experimental access to the Planck scale is effectively ruled out by this calculation, not just for our current civilization, but likely for any civilization operating within the laws of physics as we understand them. The number also reveals something important. The Planck scale is not just beyond our current technology, it is beyond any incremental improvement to current technology. Moving from the Large Hadron Collider to a Planck-scale accelerator is not the same kind of leap as moving from a bicycle to a car. It is more like moving from a bicycle to a machine that wraps around a galaxy. The gap is categorical, not merely large. This is why theoretical physics operates the way it does at the Planck scale. Since direct measurement is impossible, physicists look for indirect signatures. They search for effects that Planck-scale physics would leave on things we can measure. They look for tiny deviations in the arrival times of gamma-ray photons from distant explosions. They look for specific patterns in the cosmic microwave background. They look for mathematical consistency, theories that produce sensible answers at the Planck scale, and also reduce to confirmed physics at every larger scale. None of these indirect approaches has yet confirmed what happens at the Planck scale. They constrain possibilities. They rule out certain models. They narrow the space of viable theories. But the direct test remains out of reach. And yet there is a theoretical escape hatch, one that has been seriously proposed by physicists that would make the Planck scale accessible at far lower energies. It requires the universe to have more dimensions than the 3 of space and 1 of time that we observe. If extra dimensions exist, curled up at small scales, invisible to current experiments, they could change the effective Planck length, moving it to a scale within reach of machines we could actually build. The physics of extra dimensions is not speculation for its own sake. It is a serious attempt to make the unmeasurable measurable. And the implications, if it is right, are stranger than the measurement barrier itself. 3 dimensions of space, 1 of time. That is the universe as observed. Every direction you can move, every moment you can experience, fits into this 4-dimensional structure. Physics is built on this. Every equation, every confirmed theory, every measurement assumes these 4 dimensions. String theory requires 10 dimensions to be mathematically consistent. Some versions of string theory require 11. The extra dimensions, 6 or 7 of them, are proposed to be real but compactified, meaning they are curled up at a scale too small for current experiments to detect. Every point in what looks like a smooth 3-dimensional space would, at very small scales, have extra directions you could move in, loops too small to enter with any known particle. This sounds like a mathematical convenience, but it has a physical consequence that changes the Planck scale problem entirely. Gravity is the weakest force in nature by a staggering margin. An ordinary refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. A single proton inside an atom is repelled by electrostatic force from the neighboring proton billions of times more strongly than gravity pulls them together. Gravity is weak in a way that has no good explanation in standard physics. This is called the hierarchy problem. One proposed solution involves extra dimensions. If gravity leaks into the extra dimensions while the other forces are confined to the standard 3-dimensional surface, then gravity would appear weak in our observable dimensions, because most of its strength is being diluted across dimensions we cannot see. The actual strength of gravity across all dimensions would be far greater than what we measure. If this is true, then the effective Planck length, the scale at which gravity becomes comparable in strength to quantum effects, would be much larger than the standard Planck length. Instead of sitting at a distance 100,000 light-years of accelerator away, the effective Planck scale could be within reach of machines like the Large Hadron Collider or its proposed successors. This model, called large extra dimensions, predicts that Planck-scale physics effects would appear at energies accessible to near-future accelerators. Specifically, it predicts the production of miniature black holes in high-energy particle collisions, the same microscopic black holes that theoretically form when you try to measure the standard Planck length. The Large Hadron Collider searched for these miniature black holes. None were found at the energies probed. This does not rule out the large extra dimensions model entirely, but it pushes the effective Planck scale to higher energies than originally hoped. The search continues. Future accelerators at higher energies would probe further into the range where miniature black holes, if the model is correct, should appear. Each null result narrows the viable space of extra dimension models without eliminating the concept. The extra dimension proposal is one of several attempts to make the Planck scale physically accessible. Another approach does not involve building a bigger machine at all. It involves rethinking what information is, where it lives, and whether a 3-dimensional space with a Planck-length floor might actually be a projection of something much stranger. That idea does not come from string theory or loop quantum gravity. It comes from the mathematics of black holes. And it suggests that the Planck length marks not just the floor of space, but the resolution limit of a cosmic projection screen. In the early 1990s, a physicist named Gerard 't Hooft noticed something strange about black holes and information. The amount of information that can be stored in a region of space is normally assumed to scale with the volume of that region. Double the volume, double the storage capacity. This is how every information system humans have built works. More space, more data. For black holes, the calculation gives a different answer. The maximum amount of information that can fall into a black hole before it is saturated is proportional to the surface area of its event horizon, not the volume inside, the surface, not the interior. A black hole twice as wide has 4 times the surface area, and therefore 4 times the information capacity. the same scaling as area, not volume. This result, confirmed mathematically by Stephen Hawking's earlier work on black hole thermodynamics, suggested something radical. If the information content of a region is limited by its surface area, then perhaps all the physics happening inside a volume of space is fully encoded on the boundary surrounding that volume. The interior and the boundary carry the same information. Three-dimensional events inside the volume are redundant. They are described completely by a two-dimensional surface. Physicists Leonard Susskind and T. Hooft developed this into what is now called the holographic principle. A hologram is a two-dimensional surface that encodes a three-dimensional image. The holographic principle proposes that the universe may work the same way, that the three-dimensional reality we observe is a kind of projection of information encoded on a two-dimensional boundary. The Planck length enters this picture directly. Each unit of information on the boundary surface occupies an area of 1 Planck length squared. This is called the Bekenstein bound. The maximum information density of any surface is 1 bit per Planck area. The Planck length is the pixel size of the holographic screen. Juan Maldacena provided the strongest mathematical support for this in 1997. He showed that a specific type of quantum field theory, living on a boundary surface, is exactly equivalent to a theory of gravity operating in the volume that the boundary encloses. The two descriptions, one without gravity in 2 dimensions, one with gravity in 3 dimensions, produce identical physical predictions. This correspondence, called the anti-de Sitter conformal field theory correspondence, is the most tested and most cited result in theoretical physics of the last 30 years. What this means for the Planck length is profound. If the holographic principle is correct, then the three-dimensional space we live in is a derived quantity, a projection of information encoded at Planck scale resolution on a two-dimensional surface. The Planck length is not just the floor of the three-dimensional space we observe. It is the pixel size of the surface that generates the three-dimensional space we observe. Reality, at its most fundamental level, may be a hologram with a Planck resolution screen. This reframes the measurement barrier. The reason nothing below the Planck length can be measured is not simply because probes become black holes. It is because below the Planck length there is no additional information encoded in the boundary. The projection has no finer resolution. You are not blocked from seeing what is below the Planck length. There is nothing below the Planck length to see. The holographic principle connects to the information paradox, the question of what happens to data that falls into a black hole. And that paradox, when pushed to the Planck scale, produces the most disturbing question in modern physics. A question that Stephen Hawking spent the last decades of his life trying to answer. Information does not disappear. This is one of the most foundational principles in physics, and quantum mechanics depends on it completely. If you know the complete state of a physical system, at one moment the laws of physics allow you to reconstruct its complete state at any earlier or later time. Nothing is lost. The past is encoded in the present. Information is conserved. Black holes appear to break this rule. When matter falls into a black hole, it carries information. The specific arrangement of atoms, the spin of electrons, the state of every particle, all of it crosses the event horizon. Classical general relativity says that information is gone. The event horizon hides it. The singularity at the center destroys it, and nothing comes back. Stephen Hawking showed in 1974 that black holes slowly evaporate through the emission of radiation, now called Hawking radiation. This radiation is thermal. It is random. It carries no information about what fell in. If a black hole evaporates completely through Hawking radiation, the information about everything that ever fell in is gone permanently. This contradicts quantum mechanics, which says information is always preserved. The paradox sits at the Planck scale in a specific way. The very last moments of a black hole's evaporation are Planck scale events. As the black hole shrinks, it gets hotter and emits radiation more rapidly. The final burst of evaporation, when the black hole has shrunk to Planck size, releases the most energy in the least time. Whatever happens to the stored information, whether it escapes, whether it is destroyed, whether it is encoded in some other form, happens in those final Planck scale moments. Physicists have been arguing about this for 50 years. The debate intensified in 2004 when Stephen Hawking publicly conceded that information is probably preserved, that Hawking radiation must carry information in some subtle, scrambled form, even if the mechanism is not yet understood. He published a revised argument. Many physicists accepted it. Others remained unconvinced. The holographic principle provides a candidate mechanism. If all information about the interior of a black hole is encoded on its event horizon, on the Planck resolution surface, then as the black hole evaporates, the information encoded on that shrinking surface is gradually released into the outgoing radiation. The information escapes, encoded in correlations between different parts of the radiation that are individually random but collectively carry a pattern. Proving this rigorously requires a complete theory of quantum gravity. Without that theory, the information paradox remains formally unresolved. What is known is this: something happens at the Planck scale during the final evaporation of a black hole that either preserves or destroys information. The answer would tell us whether quantum mechanics survives at the absolute limit of physics, or whether reality has a deeper rule that overrides it. The information paradox is not just a problem about black holes. It is a test of whether the universe is fundamentally consistent. If information is destroyed, quantum mechanics fails. If information is preserved through the Planck scale evaporation process, something new and unknown is operating at the bottom of reality. Either answer reshapes physics completely, and the sharpest version of this question points directly at the beginning of the universe itself, a moment when all the matter and energy that now spans billions of light years was compressed into a space smaller than a Planck length. The Big Bang model is confirmed by multiple independent lines of evidence. The expansion of the universe, measured by the redshift of distant galaxies, the cosmic microwave background, the faint heat signature left over from when the universe first cooled enough for atoms to form, the abundance of hydrogen and helium in the universe, which matches predictions from the first few minutes of a hot, dense early universe. The model is solid. Wind the expansion backward, and the universe gets smaller, hotter, and denser. Continue winding, and you arrive at a singularity, a mathematical point of infinite density and zero size, 13.8 billion years ago. That singularity is a problem. Infinite density is not a physical description. It is a signal that the equations are broken down. General relativity predicts the singularity, but cannot describe what happens there. It is the same kind of breakdown that occurs at the Planck scale during a measurement. The math produces nonsense because it is being applied outside its valid range. The relevant question is this: at some point in the early universe, all the matter and energy now spread across the observable universe, a sphere roughly 93 billion light-years in diameter, was compressed into a volume smaller than the Planck length. Before the universe was 1 Planck tick old, it occupied a Planck scale volume. At that moment, the same problem that breaks measurement at the Planck scale also breaks the description of the early universe. Quantum mechanics and general relativity are both needed simultaneously. Neither works alone. The missing theory of quantum gravity is not just needed to describe the floor of space. It is needed to describe the first moment of the universe's existence. Loop quantum gravity addresses this directly with the Big Bounce model. If space is quantized into Planck-scale chunks, then a contracting universe cannot shrink below the Planck volume. The chunks cannot be compressed further. Instead of collapsing into a singularity, the universe reaches a maximum density at the Planck scale and rebounds outward. Our universe did not begin at a singularity. It began as the expansion phase of a previous contracting universe that bounced at the Planck limit. This model predicts specific signatures in the cosmic microwave background, patterns in the oldest light we can observe that would carry imprints of the contracting phase before the bounce. Experiments are looking for these patterns. So far, the data is consistent with, but does not confirm the bounce model. String theory handles the early universe differently. In some string cosmology models, the universe before the Big Bang was a higher dimensional space that underwent a transition, with our four-dimensional universe emerging as a kind of surface or brain within that higher dimensional space. The singularity is replaced by a transition between geometries. Both models agree on one thing: the physics of the very first moment of the universe requires quantum gravity. The Planck length is not just the smallest measurable distance in the current universe, it was the size of the entire universe at its beginning. The floor of space is the same scale as the origin of everything. And the force that makes measurement impossible at the Planck scale, gravity, was at its most extreme in that first moment. The weakest force at human scales becomes the dominant force at Planck scales, in both the early universe and in modern measurement attempts. Understanding why gravity is so weak now, when it was so overwhelming then, leads to one of the most puzzling asymmetries in all of physics. Hold a paperclip above a table and release it. Gravity, the pull of the entire mass of the Earth, pulls it down. One small refrigerator magnet, a few ounces of magnetized metal, can hold that paperclip up against the full gravitational pull of a planet with a diameter of 8,000 miles. The magnet wins easily. This comparison captures something real. At the scale of atoms, the electromagnetic force is roughly 10 to the 36th times stronger than gravity. Written out, that is a 1 followed by 36 zeros. Gravity is not slightly weaker than the other forces, it is incomprehensibly weaker. Physicists call this the hierarchy problem. No one knows why the gravitational force is so much weaker than electromagnetism. The weak nuclear force, the standard model of particle physics, has no explanation. Gravity simply is what it is. Extraordinarily weak at the scales of atoms and particles. At the Planck scale, this hierarchy inverts. Here is why. Gravity grows stronger with proximity. The closer two objects are, the stronger the gravitational force between them. And gravity couples to energy. A more energetic particle curves space more strongly than a less energetic one. At the Planck scale, the particles involved carry Planck energy. Their gravitational effect becomes comparable to their quantum mechanical effects. The force that barely registers at atomic scales becomes the dominant physics at Planck scales. More precisely, at the Planck scale, the gravitational force between two Planck energy particles equals the strong nuclear force. Gravity catches up completely. The hierarchy disappears. All forces of nature are expected to merge into a single unified description at the Planck scale. This is one of the reasons the Planck scale is considered so physically significant. It is not just the measurement limit, it is the energy scale at which all forces become equal, and at which a unified theory of all physics should apply. The standard model, which unifies three of the four forces, breaks down exactly at the Planck scale. A theory that includes gravity alongside the other forces, a theory of everything, would only need to be applied at and above the Planck scale. Below it, everything unifies. The weakness of gravity at human scales is, from this perspective, a low-energy artifact. At low energies, gravity is faint. At Planck energy, it is equal. The force we almost cannot detect at the scale of particles becomes the force that makes Planck scale measurement impossible. Some physicists find this deeply suggestive. The measurement barrier at the Planck scale is not caused by any single force acting alone. It is caused by gravity becoming strong enough to compete with quantum mechanics at the same energy scale where all forces converge. The measurement limit and the unification point are the same location. That connection may or may not be a coincidence. Physics has no confirmed answer, but it points to something important about the measurement act itself, the fact that observation at the Planck scale is not a passive process. The act of measuring changes the thing being measured in the most extreme possible way, and the principle describing that change runs all the way from the largest scales of quantum mechanics down to the absolute bottom of the universe. The act of measurement is never neutral. This has been known since the early days of quantum mechanics, but its implications at the Planck scale are the most extreme version of a principle that runs through all of physics. In quantum mechanics, a particle does not have a definite position until it is measured. It exists in a superposition, a range of possible locations, each with a probability. The measurement collapses this superposition into a single definite value. Before the measurement, the position is genuinely uncertain. After the measurement, it is fixed. The act of observing participates in creating the outcome. This is confirmed experimentally by the double-slit experiment. Fire electrons one at a time at a barrier with two slits, and they build up an interference pattern on the detector behind, a pattern that only makes sense if each electron passes through both slits simultaneously. As a wave, place a detector at one slit to observe which slit the electron passes through, and the interference pattern disappears. The electron behaves like a particle again. The presence of the observation changes the physical result. At the human scale, this effect is negligible. Measuring the position of a baseball does not change how it moves in any detectable way. The effect is there in principle but unmeasurably small. At the Planck scale, the effect is total. At the Planck scale, the energy required to make the measurement is so large that the probe destroys the space it is measuring. The act of observation does not subtly disturb the system. It collapses the system into a black hole. The measurement completely overwrites the thing being measured. The observer and the observation and the result are a single catastrophic event. This is the Planck scale measurement problem. At every other scale in physics, there is some separation between the observer, the tool, and the system being observed. At the Planck scale, these three things merge. The probe is the result, is the destruction. There is no measurement without collapse, and no collapse without hiding. Some physicists see the Planck measurement problem as a clue about the nature of reality. If observation always participates in creating outcomes, and if the Planck scale is where observation becomes maximally violent, then perhaps the observer and the universe are more fundamentally linked than classical physics ever acknowledged. This is the territory where physics, philosophy, and questions about the nature of reality begin to overlap. The confirmed version of this is simpler. The Planck scale is where the measured and the measurer become the same event. Quantum mechanics tells us that measurement is always participatory. The Planck scale tells us that at the bottom of reality, participation is everything. Nothing is neutral. Nothing is passive. Every attempt to know the universe at its finest grain changes the universe in the most permanent way possible. That reality, a universe that actively resists inspection at its own foundation, raises a question that has no scientific answer yet. What does it mean for humanity that there is a wall in reality we can never physically cross? What does it do to science, to knowledge, to the human project of understanding when we encounter a limit that is not technological, but fundamental? That question is not just philosophical. It has practical implications for how physics will develop over the next century, and what kind of knowledge we should expect to find on the other side. Science has always assumed that the unknown is reachable. Given enough time, enough resources, enough ingenuity, anything can be measured, tested, and understood. This assumption has driven centuries of discovery. It is behind every telescope built, every particle accelerator funded, every theory proposed. The frontier moves. The unknown shrinks. The Planck length challenges this assumption directly. The wall at the Planck scale is confirmed to be real in the sense that current physics cannot describe what is below it, and the energy required to test it directly exceeds any machine conceivably buildable within the constraints of known physics. But the deeper question is whether the wall represents a permanent limit on human knowledge, or just a very hard problem waiting for a smarter approach. History offers mixed guidance. There have been moments where scientists declared that a limit was fundamental, and later discoveries dissolved it. In the 19th century, Auguste Comte declared that humans would never know the chemical composition of stars. Spectroscopy proved him wrong within decades. The atom was declared indivisible. It was not. But there are also limits that have held. The speed of light has remained a confirmed maximum. Thermodynamic entropy has never been reversed. The past has never been directly observed. Some walls in physics are real walls, and the longer they hold against every attack, the more likely they represent genuine features of nature rather than temporary gaps in technology. The Planck length wall is different from all previous limits in one specific way. It is not a wall imposed by the universe against our tools from the outside. It is a wall that arises from the act of measurement itself, enforced by the laws of physics at the deepest level. Every approach to it, from every direction, using every physical principle, hits the same barrier. It is not that we lack the right tool, it is that the act of reaching for the tool triggers the barrier. For humanity, this has a specific implication. The project of physics, the attempt to describe reality at ever smaller and more fundamental scales, may have reached its experimental floor. Everything below the Planck scale will need to be accessed through theory, mathematical consistency, and indirect inference. Direct measurement is off the table. This shifts the nature of fundamental physics. Confirmation through experiment, the gold standard of science since Galileo, cannot apply below the Planck scale. A quantum gravity theory will need to be confirmed through its predictions at measurable scales, through the cosmic microwave background, through gravitational wave signatures, through the behavior of black holes, rather than through direct Planck scale tests. The confirmation will be indirect. This does not mean physics stops. It means the tools of physics evolve. Mathematical elegance, internal consistency, and predictive power at accessible scales become more important. The gap between theory and testability becomes permanent at the bottom. What lives below the Planck length, what the universe actually looks like at its finest grain, remains the deepest open question in all of science. And it forces the most fundamental question of all. Is the Planck length the real wall built into nature, or is it the edge of everything our mathematics can reach? These are different things, and the difference matters enormously. Two possibilities sit at the center of everything discussed so far, and physics cannot currently distinguish between them. The first possibility. The Planck length is a genuine feature of nature. Space is quantized. Distance stops below this value. The universe has a pixel limit. Asking what exists at a finer resolution is like asking what color is north. The question has no answer because it is not a valid question. The wall is real. The second possibility, the Planck length is the edge of our mathematical framework, not the edge of nature. Space and time may continue smoothly below the Planck scale, richer and more detailed than anything we can currently describe. The wall is not a feature of reality. It is a feature of the equations we are using, which break down at that scale the same way Newtonian physics breaks down near the speed of light. Not because reality ends, but because the theory does. These two possibilities have different emotional weights. The first is more disturbing. It says the universe is finite in its detail, that beneath the apparent complexity of matter and space, there is a coarse pixelated structure with no further resolution. Reality is a low-resolution image when you zoom far enough in. The second is more familiar to the history of physics. Every time equations broke down in the past, better equations replaced them and revealed more structure underneath. Newtonian mechanics broke near the speed of light, and special relativity showed a richer structure underneath. Classical physics broke at the atomic scale, and quantum mechanics showed a richer structure underneath. The Planck breakdown might be the same, a sign that better equations are waiting, not that reality ends. The strongest argument for the true wall is convergence. Multiple completely different theoretical approaches, string theory, loop quantum gravity, the generalized uncertainty principle, the holographic principle, all independently arrive at the Planck length as a meaningful boundary. They disagree about what the boundary means and what is on the other side. But they all agree the boundary is there. That convergence from different mathematical directions is taken seriously by physicists. The strongest argument against the true wall is the absence of confirmed experimental evidence. No experiment has directly probed the Planck scale. Every claim about what happens there is theoretical. The convergence of theories is a convergence of models built on the same underlying assumptions, and those assumptions might be wrong. A future theory might dissolve the Planck barrier entirely. Physicist Sabine Hossenfelder and others have argued that the apparent universality of the Planck limit may be a consequence of theoretical bias rather than physical reality. That theories are arriving at the Planck length because they are built from the same three constants, not because the universe is actually pixelated at that scale. The debate is live, the question is open. Physicists on both sides are serious, well-credentialed, and working actively. What makes the question strange is that it may be permanently unanswerable by direct experiment. The measurement barrier described throughout this script means that the only way to confirm whether the Planck length is a true wall is to probe below it, which is exactly what the wall prevents. The question guards itself. The answer hides behind the barrier the answer is about. This is the final frontier of physics, a wall that may be a true boundary of reality, or may be the edge of our understanding. A question that cannot be answered by going there, because going there is what the question is about. And that final paradox, the universe protecting its own deepest secret by making curiosity itself the barrier, is where physics and wonder become the same thing. Everything comes back to this. For 33 chapters, the story has moved in one direction, downward, from the visible world, through atoms, through quarks, through the proton, down past every scale where physics works, to the point where the math breaks and the measurement fails, and the theory runs out of answers. The Planck length sits at the bottom of that descent, like a locked door. But a locked door can mean two things. It can mean the corridor ends there, or it can mean there is something behind it that the door is protecting. Physics currently has no way to tell the difference. The experiments looking for indirect evidence are running. Gamma-ray telescopes scan the sky for tiny delays in photon arrival times that would signal quantized space-time. Gravitational wave detectors look for signatures of quantum gravity effects encoded in the geometry of space-time. The cosmic microwave background is mapped with increasing precision, searching for patterns that a pre-Big Bang contracting phase would have left. None of these searches has produced a confirmed detection of Planck-scale physics. None has ruled it out either. The mathematical approaches are also advancing. The correspondence between boundary quantum field theories and bulk gravity theories, the mathematical result from Maldacena, has been extended and tested in dozens of different settings. It remains the best tool for probing quantum gravity indirectly, and it continues to produce results consistent with the holographic picture. String theory and loop quantum gravity have both matured considerably since their early proposals. Neither has produced a confirmed experimental prediction unique to itself. Both remain viable. Both continue to generate new mathematics and new ideas. The competition between them is productive, even without a decisive experiment. New frameworks are also emerging: causal dynamical triangulations, asymptotic safety, causal set theory. Each approach the Planck scale from a different angle. Each produces a slightly different picture of what the floor of reality looks like, and each struggles with the same fundamental problem. Predictions are hard to test when the scale of the physics is 17 orders of magnitude beyond the most powerful machine ever built. The question of whether the Planck length is a true wall or the edge of our math is, in one sense, a question about the nature of mathematical limits in physics. Every time a theory breaks down in the past, the breakdown was a signal, not that reality ended, but that the theory needed replacement. The singularity in general relativity breaks down inside black holes. The Planck scale breakdown in quantum field theory produces infinities. These breakdowns are features of theories, not features of reality. The possibility that the Planck breakdown is different, that this time the breakdown is real, that space genuinely ends at this resolution, is supported by the unusual nature of the barrier. It does not break down in one theory, it breaks down in all theories simultaneously. Every approach to the Planck scale from every direction produces the same result: nonsense, infinities, collapse. That universality is unusual, but universality is not proof. It may mean the universe is pixelated. It may mean our theories all share the same blind spot. The question will not be answered in this generation. It may not be answered in the next. The scale is too far beyond reach. The indirect evidence is accumulating slowly. The theoretical work continues, and the wall stands, patient and unchanging, at the absolute bottom of measurable reality, waiting for a question sharp enough to get through. Every civilization that has ever looked up at the sky has found a boundary it could not cross. For most of human history, the stars were fixed points in a black dome overhead. The boundary was the dome. Then telescopes revealed that the stars were distant suns. The dome dissolved, and the universe expanded beyond imagination. A new boundary appeared, the edge of the observable universe, the sphere beyond which light has not had time to reach us. That boundary holds, but within it, the expansion of knowledge has been continuous and accelerating. The Planck length is a different kind of boundary. Previous boundaries were set by distance, things too far away to see, too faint to detect, too early in cosmic history to observe. The Planck boundary is set by scale. It is not across the universe, it is beneath everything. It is inside the atom, inside the proton, inside the quarks, deeper than any instrument has ever reached. And it is everywhere simultaneously, woven into the fabric of every point of space, at the finest grain. The physicist Richard Feynman once said that the most remarkable discovery in all of science is that nature obeys mathematical laws. The Planck scale is where those mathematical laws break, where they run out, where the laws themselves seem to fail. And that failure is not a defeat for science. It is the clearest possible signal that something profound is still missing from our understanding. The history of physics is a history of following breakdowns. Every time the math failed at a new scale, the failure was the discovery. The failure of Newtonian mechanics at high speeds led to relativity. The failure of classical physics at atomic scales led to quantum mechanics. The failure of physics at the Planck scale may lead to something that reshapes both of those frameworks entirely, a theory so different from what exists today that it is currently unimaginable. What that theory would look like is genuinely unknown. It might describe space and time as emergent phenomena, things that appear continuous and smooth at large scales, but are built from some deeper, discrete, non-spatial substrate. It might reveal that the three dimensions we experience are a low-energy shadow of a higher dimensional reality. It might show that the Planck length is the resolution of a holographic encoding, and that what we call space is information processing on a two-dimensional surface. Or it might dissolve the Planck barrier entirely and show that the universe goes deeper than any current theory imagines. The question still matters for a reason that goes beyond physics. Every time humanity has encountered a wall and kept pushing, the wall has either opened or revealed something fundamental about the nature of the universe. The Planck wall has been standing for over a century. Physicists have pushed it with mathematics, with particle accelerators, with gravitational wave detectors, with gamma-ray telescopes. It has not opened. It has revealed that the two greatest theories of physics are fundamentally incomplete. That is already a discovery. The Planck length is the address of the next revolution in physics, the next Einstein, the next Heisenberg. The next Wheeler is somewhere right now, possibly young, possibly working on something that looks unrelated, building the mathematical tool that will finally describe what happens at that scale. The tool does not exist yet. The revolution has not happened yet. The wall still stands. And that is exactly why it matters. A universe with no remaining mysteries would be a smaller universe. The Planck length is proof that the largest mystery in all of physics fits inside a space trillions of times smaller than a single atom. The universe hid its deepest secret at the smallest possible address, and it is waiting.